Okay, guys, welcome. Today we're going to talk about functions and function notation, right? So we'll talk about specifically what a function is, and then we'll talk about also how you can typically see functions written and how to tell if equation represents a function, okay? So the equation that we're going to start with is y equals 2x plus 3, right? And you can think of this as a rule that assigns a value for a y value for every value of x, right? And of course, you can think of this sort of schematically as well, where you have a set x denoting the set of values that you're allowed to assign to x. And of course, a set y could denote the set of values that the equation assigns to y, right? Now, what makes a function is a particular rule that assigns exactly one y for any x value, all right? So what we're really saying here when we have a function is that it's a rule that assigns each x value to exactly one y value, right? So let me just comment on that a little bit more before we talk about the other things. So when you have a function, if you have an x value and you plug that into a function, you cannot get more than one y value out. You get one y value. Not more than one, right? So in one of the, and actually two of the examples in the previous video, we looked at the graph of two equations that were not functions, right? Because if you had repeating x values, basically. Now, that's not to say that you can't have this. So just keep in mind that you're allowed to have something like when x equals 3, y equals 4, and when x is negative 2, y equals 4. This is okay because you still have x going to exactly one y value, even though that y value is repeating. That's totally fine. You just can't have x equals 2 leading to y equals 2 or y equals negative 2 or something like that, right? That you can't have. Okay, now some other terminology that you could see is that whatever the y value that comes out, that is sometimes called the image of the x value. And we call the set x as the domain, but I usually like to think of the domain as all possible x values that you can plug in. Right. So what I mean by that you can plug in is that there's no x values that cause division by 0 or any weird things like that. And then the range is all possible y values that can come out, or that can be reached by a certain x value. All right, so that's some terminology on functions. Okay, now one thing that many people find it convenient to use is to think of a function as sort of like this Dr. Seuss looking machine, right? So if you drop an x value in here, right, and you multiply the x value by 2 and then add 3, then out is only going to come one y value. Right? You can't have it spit out more than one y value. And if it does, then it's no longer a function. Right? Now, since x is another thing that we should mention here is that since you're allowed to pick whatever x you want to drop in we usually refer to x as the independent variable, right? But you can't just have any value of y drop out that you want. It depends on what x you threw in there, right? So we'll call y the dependent variable. All right, so that's some terminology that's sometimes used as well. Okay, so now that we've talked a little bit about functions, we can talk about how to tell if a certain equation represents a function, right? And that's the idea of the vertical line test, right? And the vertical line test states that if any vertical line touches the graph of an equation in more than one point, then the equation is not a function. We'll sort of take a look why. So we're going to look at the two equations, y equals x squared and x equals y squared. Now, if you plot out a table of values, just for time's sake, I'm just going to sort of give you the general picture. But if you plot a table of values, you'll find that you'll get something that looks like this for both of these. So y equals x squared looks something like this, where x equals y squared is sort of this thing on its side. Okay. Now let's go ahead and we'll employ the vertical line test. So now if you put a vertical line on this graph anywhere on this first y equals x squared graph, you're only going to hit the graph one time, right? So this is a function. Right? Whereas on the other hand, if you draw a vertical line almost anywhere, you're going to hit it in more than one spot, right? You're going to hit it here and you're going to hit it here. So since that happens, this is not a function. And of course, you really only need that to happen once. It doesn't matter that I can draw basically any vertical line and I'm going to hit more than once. You just need to be able to come up with one, right? Now, why does this work? Well, think about what a vertical line is, right? What's always the same on a vertical line? The x value is always the same. All right. So if the x value is always the same, that means that if I only find a piece of the graph one time for that x value, I only have one y value that comes out, which is exactly what we're looking for a function, right? However, on this one, we're saying that, say, if this represents x equals 2 or something, then that means that we're getting two y values out. We're getting like y equals 4 and y equals -4, which is precisely what we don't want. All right. So that's how you can use the vertical line test to quickly check if a given equation represents a function or not. So you can graph the equation using a table of values and then use the vertical line test. Okay. Now, this is something that I sort of went into detail a little bit in the previous slide. But if you're looking at the domain of a function, we say that that's the set of all real numbers for which the function is defined, right? Where if you plug in an x value, you get a y value to come out. And I usually, like I said, I refer to this as all possible x values, right? So any x value that wouldn't cause something weird to happen, like division by 0, or like a square root of a negative number or something like that, right? And then, of course, the range is a little bit harder to find, but it's all the y values that can occur for a possible, basically all possible output values, right? Or all possible y values. All right. Now, the reason why this is a little bit harder to tell is because you have to be either very comfortable with how certain functions behave, or you have to graph it and then study the graph. Okay, but let's go ahead and we'll take a look. So we want to graph each of these, and if the correspondence determines a function, we'll find the domain and range. Now, in each of these, they're kind of handing you the domain, right? If they specify what x has to be, that is your domain. Right? So in part A, they're telling you that x has to be between 0 and 5. And for part B, they're telling you that x has to be between -3 and 3. So they're already handing you the domain there. But let's go ahead and we'll take a look. Okay, now for part A, and again, we're going to assume that we don't know any tricks for graphing, so we're just going to use a table of values. Now I have y by itself, so I should use values of x to test, but my x is only between 0 and 5, so I shouldn't use -2 or -1. So we can test like 0, 1, 2, 3, 4, and 5, and that would sort of include everything that we would want. Now, if I plug in 0 for x, I'm going to get 4. If I plug in 1, I'm going to get 5. If I plug in 2, I'm going to get 6, and so on and so forth. So now the graph of this thing right? And I need to go out to 5. And I probably need to make this a little bit higher. It needs to go up to 9. 3, 4, 5, 6, 7, 8, 9. Okay, so it looks like I have 0, 4, 1, 5, and each time I'm just going to move to the right one and up by 1. All right, we'll kind of just make this look a little better. All right. So since we're just between 0 and 5, there's no arrow here. It's just these 6 points all connected together. Okay. So now, of course, the domain was handed to us. The domain was just 0 to 5. And of course, you could put this in interval notation by using a bracket for both. Okay. Now the range is all your possible y values. Now we have the graph, so we're going to use that to our advantage. All right. To find the range, you need to find your smallest y value to the largest y value. All right. Which you can think of as what's the lowest point on the graph, what's the highest point on the graph. Right. And of course, if you would need things in between to be filled in, but in this case, we do have that. So your lowest y value is here. And your largest y value is here. And since everything is in between is filled in, we can say that our range is from 4 to 9, because those are all the y values that come out. Okay, let's look at part B. So part B, we have y equals x squared minus 4, and we're told that x should only be between -3 and +3. Okay, so let's go ahead and we'll make our table of values here. And we'll go ahead and we'll just test everything in between here since it's fairly doable. Okay. Now, if we plug in a -3, we get a -3 squared, which is +9, and then -4, we'll get a 5. All right. Then if we plug in a -2, we'll get a 4 minus 4, which is 0. -1 squared is 1 minus 4 is -3. And when I plug in 0, I get a -4. And then we just start to go back up again. So this is -3, this is 0, and this is 5. Okay, so we got to go from -3 to 3. Okay, so it looks like my points are -3, 5, so something like this. -2, 0. -1, -3. And 0, -4. And then sort of the same thing on the other side. So we get something like this. And I should not use the arrow, right? Because this is only from -3 to 3. So this stops here. Okay, so of course our domain again was given. And if we wanted to, we could say that that's -3 to 3 in brackets. Now for the range, again, what's our lowest y value? Our lowest y value is here, and that y value is -4. So it starts at -4. And then what's my largest y value? My largest y value is here or here, but they're the same. And of course, that's 5. So your range here is -4 to 5. Okay, so hopefully that's not too bad. Okay, now in this example, we have a couple of graphs plotted for us, and we just want to be able to determine if they're functions. So now the hard part's done for the vertical line test. They already handed us the graphs. We just have to apply the vertical line test now. Now on the first one, if I draw a vertical line anywhere, I'm only going to hit one time. So this is a function. However, in the second one, I could drop a vertical line here, and I'm going to hit in 3 spots. So this is not a function. Right, and then of course, the circle, although it looks nice, is surprisingly not a function because you intersect in 2 spots. So a circle is also not a function. All right, so that's just a little bit of extra practice with the vertical line test. Okay, so now we can talk about some special function notation that's used, right? And this sort of gives us a nice convenient way of writing a function out, right? So if we had the equation y equals 2x plus 3, we can write that in function form by replacing y with f of x. Right, so it's like f and then inside parentheses an x next to it. And we read that as f of x, which just means that y is a function of x. Right? And of course, we say that f of x is the output corresponding to the input x. Right? So in equation form, you would need to say something like find y when x is 5. But in function notation, you could say the equivalent thing by just saying find f of 5. And that means replace x with 5 and see what you get. Right? So if we want to evaluate a function, what we do is we just take whatever value is inside that parentheses and we plug it in. All right, so let's do a couple of examples of that. So in part A, we have that f of x is 2x squared minus 2x plus 1. Right? And we want to find f of -1. Well, to find f of -1, I just need to replace anytime I have an x with a -1. So I'm just going to go ahead and we'll plug that in there. Right? And you always want to plug in your x inside parentheses, right? Just to be sort of careful here. All right. But now when we simplify, we just do PEMDAS, right? So first we'll handle the exponent. This will become a 2 times +1. All right, and then we get the -2 times -1, so +2. So then this is going to become a 2 plus 2 plus 1, so we get a 5 here. Okay. In part B, we have that f of t is equal to 3t minus 1. And we want to find f of a squared. All right, so then we have a 3, and I'm going to open up parentheses for my t, and I'm replacing it with a squared. Well, this is just 3a squared if I distribute and then minus 1. And since we don't know what a is, that's the best we can do. So we just replace t with a squared there. Okay, part C, we have f of u is equal to u to the third plus 3u minus 4. And we want to find f of negative 2. All right, so I need to, again, replace my u with a negative 2. So I'm just going to open up a couple parentheses here. And we'll plug in my negative 2. Okay, so now if we simplify, this will become negative 2 to the third. We'll get a negative 8. And then 3 times negative 2, we'll get a minus 6. And then minus 4. So it looks like we're going to get a negative 18 here. Okay, and then finally part D, we get that f of t is equal to t squared plus 1. And we want to find f of t minus 1. So now, again, I'm replacing t with t minus 1. So I need to replace inside parentheses t with t minus 1. Well, now we can use that special formula for squares, or you could just write this twice and FOIL it, but you're going to get that this is t squared minus 2 times the product of t and 1, which is just 2t, and then plus 1 squared, which is 1. Okay, and then plus 1. So it looks like we're going to get a t squared minus 2t plus 2. Okay. Let's look at another example involving that. Okay, so now in this one, we have that f of x is always going to be given by x squared minus 1. Okay, so in part A, f of negative 2 is a negative 2 squared minus 1. So we get a 4 minus 1, so we get a 3. Okay, in part B, we want to find f of a plus h. So I'm replacing x with a plus h in parentheses, all squared, and then minus 1. So again, using our special formula, this is the first term squared, so a squared plus 2 times the product of a and h, so that's just 2ah, and then plus h squared minus 1. Okay, now in part C, we're finding f of a plus h, so the thing that we just found, minus f of a, right? So this is f of a plus h. So let's not do the work again. This is just going to give us a squared plus 2ah plus h squared minus 1. Right? Now I just, in this parentheses, have to put f of a. Right? Well, f of a is just going to be a matter of replacing x squared with a squared, right? So this is minus an a squared and then minus 1. Okay, so when I distribute this negative, my a squareds are going to cancel, and so is my 1, right? And you're going to get a 2ah plus h squared. Okay, so that's that example. Now in part D, we have 2 times f of x. So that just means I need to take 2 and multiply it by my f of x, which is x squared minus 1. And once we distribute, we'll get a 2x squared minus 2. Okay, part E, we have of f of 1 over x. So again, I'm just replacing x now with 1 over x. And if we square 1 over x, we're going to get a 1 over x squared, and then just minus 1 again. Okay, and then last but not least, part F, we need to find f of 0. So just replace x with 0. 0 squared is 0. And then if we subtract 1, we get a negative 1. Okay, so there's a couple more examples of evaluating a function. Okay, so in the next example, we have the relationship between Fahrenheit and Celsius temperature, right? So you have that F of C is equal to 9/5C plus 32. Okay, now we want to find the Fahrenheit temperature corresponding to Celsius of 37. So part A, and again, our function is giving us Fahrenheit when Celsius goes in. Right? So we need to find, basically, we're finding F of 37, and that will give us Fahrenheit. So we would have 9/5 times 37 plus 32. All right, so if we think of 37 as 37/1, then we get a 9 times 37, which let me do on the side here, 3 times 9 times 37 will give us a 333/5 plus 32, which if we write 333/5 as a decimal, we're going to get a 66.6 repeating plus 32. So then that's going to give us a 98.6 repeating here, it looks like. Okay. Part B, we want to write C as a function of F. So now what this means is that we have basically that F is equal to 9/5C plus 32, and we want to solve this for C now. So if we start with F equals 9/5 C plus 32, and we want to get C by itself, we would subtract 32, and we would get that F minus 32 is equal to 9/5 times C. And now we can multiply both sides by the reciprocal of 9/5. We can multiply both sides by 5/9. And we'll get that C is equal to 5/9 times F minus 32. So now we have a function where if I plug in Fahrenheit, I'll get Celsius to come out. So we can write this as C of F is equal to 5/9 times F minus 32. Okay, now in part C, we want to find the Celsius temperature that corresponds to Fahrenheit of 212. Right? Now, if you remember from your high school, probably would talk about this in chemistry, maybe. You know that the boiling point of water in Celsius should be 100 degrees. So we should expect 100 to come out, but let's go ahead and we'll do it. So if we find C of 212, we get a 5/9, and replacing F with 212, and then minus 32. So if we simplify those parentheses, we're going to get a 180, right? And then, of course, if we think about 180 divided by 9, then that's going to give you a 5 times 20, which, of course, is 100. All right, so that's the answer that we should expect. Okay, let's look at, I think this is the last, one last example in this section, and we'll wrap this video up. So in this example, we're supposing that an object is dropped from a fixed height. All right, so then if you neglect air resistance, then the distance that the object has fallen after t seconds is a function of t, and it's given by S of t equals 16t squared. Okay, so now of course we want to find the distance traveled by an object when t is as follows, right? So now, and I think this is a typo, we really should have S or T, is as follows. Because if they're giving you A is 64 feet, then the distance is really the S value, right? So here we would want to solve 64 is equal to 16 t squared, right? So we would want to find the time corresponding to t here, right? So to find t, we would divide both sides by 16, and we get a 4 is equal to t squared. So then this tells you that t, once you square root, is either 2 or negative 2. But of course, you can't have negative time, so we want this one. Okay. Similarly, part B, we're given feet, so this is an S value. So we want to solve 256 is equal to 16 t squared. So if we divide each side by 16, let's see, that will give me a t squared is equal to, let me just double check this so I don't tell you the wrong thing. So 256 by 16 will actually give you 16, yeah. Okay, and then of course you get t is equal to 4, negative 4, but of course we want just the positive 4. Okay, now in part C, finally, now they're giving you a t value. They're giving you 5 seconds, so that's equal to t. So now we want to find what S of 5 is, right? So 16 times 5 squared. So we get 16 times 25, which if you multiply those together should be 400. So then that means that after 5 seconds, it's fallen 400 feet. Okay, so that wraps up this video on functions and function notation. I hope you enjoyed, and I will see you next time.